Hello, my name is Jacob Magnon, and this is the second lab of the year for Physics 1, Motion of a Falling Object. Let's get straight into it. So for this lab today, we're going to be looking at first the fundamental principles and forces that we need to know going into it, and then talk about some of the process and the steps that we need to take in order to evaluate these principles in action. We're going to take a video of a ball falling and then track it using online software, and then make a couple computational models based off of the forces that we expect the ball to experience. Then we'll graphically compare these models and the initial video and make some analysis on the similarities and differences. Finally, we'll answer some questions about the lab. As far as the purpose for this lab, what we really want to do is demonstrate the properties of Newton's second law. We're going to observe how motion occurs as a result of net force, and we'll be looking at an object falling straight down, which means we're going to be looking at the forces of gravity and drag, and then we're going to create some simulated models of the falling object to see how these forces interact. As our physics principles, looking at the momentum principle, if we divide everything by the mass, we'll get something that you guys should be familiar with, which is our velocity update equation, Vf equals Vi plus F net over m delta t, which will be important later. Looking at gravity, this is simply m times g. However, because it is pulling our object down, we'll put a negative in front of it. And then looking at drag, this is going to be equal to negative b times velocity squared, where b is just a proportionality constant. Looking at a diagram of our forces, this is our ball or our system. The force of gravity is going to be pulling it straight down, of course, and the force of drag is going to be acting in the opposite direction. And so over time, drag will increase to equal the force of gravity, and at this point, our velocity will be what we call terminal velocity, which is something we'll see later on in this lab. Here we are looking at our position versus time graph of the falling object, and as you can see, as time goes on, this slope kind of becomes more linear. And if gravity was the only force, we would expect this slope to keep curving and becoming steeper. However, the force of drag kind of counteracts this gravitational force, which is why we get this kind of constant velocity towards the end. For our first computational model, we're actually only going to be looking at the gravitational force, and we can see this right over here, where F net is equal to the mass of the ball times gravity, of course in the negative direction. And then we're going to have this velocity update equation, which we stated before, Vf equals Vi plus F net delta t, and then the position update equation, which is Rf equals Ri plus V delta t. And these are both seen down here in these two lines of code. So for our second computational model, we'll be looking at net force is equal to both gravity and drag. And for our drag, the equation for that is simply negative b times velocity squared. And all these can be shown. B is up here, and the net force is down here. And as you can see, all we've done is added the force of drag onto our initial net force equation, which was gravity. Okay, so looking at this graph here, the orange line is our actual position in time. The gray line is going to be our first model, which only included gravity, and our yellow line is our second model, which included the force of drag as well. So looking at this, you can see that the gray line really starts to diverge from the other two over time, and that's because the velocity here keeps on increasing without any drag force. However, the other two lines do experience this drag force, and the velocity over time will become much more linear and come to a constant value. The questions for this lab, what does it mean? So as we saw, the ball started to reach a constant velocity over time, and this is because we reached something known as terminal velocity, which is where drag is equal to gravity. And at this point, we have zero net force, so there's no reason for the ball to continue to increase in velocity. Now, what if the object was thrown down instead at the start? If this were the case, our initial velocity would not be zero, and it could be moving faster than terminal velocity. However, the force of drag would be so high that the ball would start to slow down until drag and gravitational force reach equilibrium once again. Anyways, that's about it for this lab. Thanks.